Welcome to IT Essentials 8. In this chapter, we're diving into the basics of personal computer hardware. We'll explore the key components that make up a PC, how they work together, and why understanding them is essential for anyone interested in technology. Let's get started. In this chapter, we're diving into personal computers, what they're made of, and how to keep those parts safe. We'll cover the basics of electrical and electrostatic safety, so you know how to handle components without damage. Then, we'll explore each key part inside a PC, from cases and power supplies to motherboards and CPUs. We'll also look at different types of memory, adapter cards, and storage devices like hard drives and SSDs. This sets the foundation for understanding how computers work. Let's continue exploring the key parts of a PC. We'll look at optical storage devices, things like CDs and DVDs that store data using lasers. Then, we'll cover ports, cables, and adapters, the connectors that link everything together. Next, we'll talk about input devices, like keyboards and mice, and output devices, such as monitors and printers. Finally, we'll dive into disassembling a PC, learning about the tools you need and how each part fits together. Let's start with the personal computer, a device that changed everything. It put power in our hands, right on our desks. Suddenly, computing wasn't just for specialists or big companies. It became personal, accessible, and essential. This shift opened the door to new ways of working, learning, and creating. Understanding the personal computer is key to seeing how technology reshaped our world. Let's take a moment to explore what's inside a computer. We'll break down the key components that make it all work, from the brain, or processor, to the memory that holds information temporarily. We'll also look at storage, where data lives long-term, and the parts that let us interact, like the keyboard and screen. Understanding these pieces helps us see how computers do so much, so fast. We need to follow electrical safety guidelines to keep ourselves and our equipment safe. Electrical devices have specific power needs. For example, AC adapters are designed for particular laptops. Using the wrong adapter can damage both the adapter and the laptop. Printers also have parts, like power supplies, that carry high voltage. It's important to check the printer manual to know where these high-voltage components are before you start any work. Safety first, always. Electrostatic discharge, or ESD, can sneak up on us when a buildup of static electricity jumps between surfaces. It's invisible, but it can seriously damage computer components if we're not careful. To keep things safe, we follow some simple steps. We keep parts in anti-static bags until installation. We work on grounded mats, both on benches and floors. And we wear anti-static wrist straps when handling sensitive hardware inside computers. These precautions help us avoid costly damage and keep everything running smoothly. In this lab, we're focusing on safety, a crucial part of working with computer hardware. We'll cover 4 key areas. First, personal safety, how to protect yourself while you work. Then, electrical safety, because electricity demands respect. Next, fire safety, knowing how to prevent and respond to fires. Finally, compliance with government regulations, making sure we follow the rules that keep everyone safe. Together, these steps create a safe environment for building and servicing computers. Now, let's take a closer look at the core parts that make up a personal computer. These are the building blocks, the components that work together to bring your machine to life. From the processor that handles calculations to the memory that stores information temporarily, each piece plays a critical role. Understanding these components helps us see how a computer functions as a whole and sets the stage for everything we'll explore next. When it comes to computer cases, manufacturers often use their own naming styles. You might hear terms like super tower, full tower, mid tower, mini tower, or even cube case. Each name hints at the size and shape of the case. The case itself is the shell that holds everything inside: the power supply, motherboard, CPU, memory, drives, and cards. When we talk about form factor, we mean the physical design and layout of the case. Common desktop cases come in a few main shapes and sizes, each suited to different needs. Let's talk about power supplies, the unsung heroes inside our computers. They take the AC power from the wall and convert it into the lower voltage DC power that all the internal parts need to run. We started with the advanced technology, or AT, which powered older systems. Then came ATX, an updated version that improved things. Today, the most common is ATX12V, and for high-end desktops and servers, there's EPS12V, built for heavy-duty performance. These form factors shape how power supplies fit and function inside our machines. A power supply isn't just one plug, it has several different connectors. Each one powers a specific part inside the computer, like the motherboard or the disk drives. For example, there's the 20 or 24 pin connector that usually hooks up to the motherboard. Then, SATA and Molex connectors power storage devices. You'll also find smaller connectors like the Berg, auxiliary power connectors, and PCIe connectors for graphics cards. Each plays a key role in keeping the PC running smoothly. A computer can handle small ups and downs in power, but a big swing can make the power supply fail. Power supplies come in different types: single rail, dual rail, or multi-rail. A rail is basically the circuit board inside the power supply where the cables connect. These connectors deliver different voltages, usually 3.3 volts, 5 volts, and 12 volts. The lower voltages power digital circuits, while the 12 volts run motors in disk drives and fans. The motherboard is the heart and backbone of any computer. Think of it as a printed circuit board, packed with electrical pathways called buses. These buses connect all the important electronic parts, letting them communicate and work together. Some components are soldered right onto the board, while others plug in through sockets, expansion slots, or ports. Without the motherboard, none of the pieces would fit or function as a whole. It's where everything comes together. Let's break down the major components you'll find on a motherboard. At the heart is the CPU, the brain of the computer. Then there's RAM, which acts like short-term memory, helping your system run smoothly. Expansion slots let you add extra cards for graphics or sound. The chipset manages data flow between parts. You'll also see the BIOS and UEFI chips. They help start your system. SATA connectors hook up storage drives, and internal USB connectors link other devices inside the case. These parts work together to keep everything running. Let's talk about the chipset, the set of integrated circuits on the motherboard that manage how all the system hardware talks to the CPU and the rest of the board. Most chipsets break down into two parts. First, the North Bridge, which handles high-speed connections like RAM and the video card. Then there's the South Bridge, which deals with slower devices, things like hard drives, USB ports, and expansion slots. Together, they keep everything running smoothly. The motherboard's form factor is more than just size. It sets the stage for how everything else fits together. It decides how components connect, what kind of power supply you'll need, and even the shape of your computer case. There are three main types you'll encounter: ATX, Micro ATX, and ITX. Each one has its own footprint and purpose, shaping the whole build from the inside out. Understanding these form factors helps us make smarter choices when assembling a PC. Let's talk about the CPU socket. It's the crucial link between the motherboard and the processor. Modern CPUs and their sockets come in two main styles. First, there's the pin grid array, or PGA, where the pins are on the underside of the processor and slot into the socket. Then there's the land grid array, or LGA, where the pins actually sit inside the socket itself. At the heart of it all, the CPU is a tiny microchip that interprets and executes commands, making it the brain of the computer. When it comes to keeping our computer components cool, there are two main approaches: passive and active cooling. Passive cooling relies on methods that don't need power, like slowing down a component or adding heat sinks to draw heat away. Active cooling, on the other hand, uses powered devices, like case fans, to move air and lower temperatures. Both methods are essential because cooler components perform better and last longer. So, understanding these cooling systems helps us keep our PCs running smoothly. Let's talk about two key types of computer memory: read-only memory, or ROM, and random access memory, or RAM. ROM is permanent storage, like a ROM chip, holding essential instructions. RAM, on the other hand, is temporary. It's where data and programs live while the CPU is using them. RAM is volatile, meaning it loses its contents when the power's off. Adding more RAM usually boosts performance, but how much you can add depends on your motherboard. All memory stores data in bytes. That's 8 bits, each is 0 or 1. Let's take a closer look at the different types of read-only memory, or ROM. We start with basic ROM chips. These are programmed during manufacturing and can't be changed. Then there's PROM, which can be programmed once after production. EEPROM takes it further. It can be erased with ultraviolet light and reprogrammed. Finally, EEPROM chips can be erased and rewritten electrically, making them more flexible. These variations play key roles in how PC components store and manage data. When we talk about RAM, or random access memory, we're really looking at several types that serve different roles in computing. It starts with dynamic RAM, or DRAM, which is the basic form. Then there's static RAM, or SRAM, which is faster but more expensive. From there, we move into synchronous DRAM, or SDRAM, which syncs with the system clock for better performance. The DDR family, DDR, DDR2, DDR3, DDR4, and now DDR5. Each step up brings faster speeds and improved efficiency. We also have GDDR, designed specifically for graphics processing. Together, these types make up the memory backbone of modern PCs. Memory speed plays a crucial role in how much data a processor can handle at once. The faster the memory, the smoother everything runs. Static RAM, or SRAM, is usually the quickest. That's why it's used for cache memory, right next to the processor. Memory chips are grouped on modules which plug into slots on the motherboard. You might have heard of different types: DIP, SIM, DIMM, and SODIMM, each designed for specific uses and form factors. This slide helps us understand the building blocks of computer memory. Let's talk about the 3 most common types of cache memory. First, there's L1 cache, which is built right into the CPU itself. Then we have L2 cache. It used to sit on the motherboard, but now it's also integrated directly into the CPU. Finally, L3 cache is found mostly in high-end workstations and server processors. Cache memory uses static RAM, or SRAM, which is the fastest type of memory. This speed matters because it directly affects how quickly the processor can handle data and instructions. When it comes to memory errors, the computer has a few ways to catch and fix them. First, there's non-parity memory. This type doesn't check for errors at all. Then we have parity memory, which adds 1 extra bit to every 8 bits of data, just to spot errors. Finally, ECC, or error correction code memory, goes a step further. It can find multiple errors and even fix single-bit mistakes. These methods help keep our data reliable inside the memory chips. Adapter cards are a simple way to boost what your computer can do. They add controllers for specific devices or swap out ports that aren't working right. Some common examples include sound adapters, network interface cards, and wireless NICs for connectivity. You'll also find video or display adapters, capture cards, TV tuner cards, USB controller cards, and eSATA cards. Each one expands your PC's capabilities, letting you customize or repair your system without replacing the whole machine. Let's talk about expansion slots, the connectors on a motherboard where we install adapter cards. These slots come in several common types. There's PCI, Mini PCI, PCIX, and PCI Express, or PCIe, which is the most common today. We also have riser cards, which let us add more cards in tight spaces, and the accelerated graphics port, or AGP, which was popular for graphics cards before PCIe took over. The key is that the adapter card's connector has to match the slot type exactly. When we talk about data storage devices, we're really looking at the kind of media they use to hold information. There are 3 main types: magnetic, like hard disk drives and tape drives; solid state, such as solid-state drives; and optical, which includes CDs and DVDs. All of these drives offer non-volatile storage, meaning the data stays put even when the power's off. Some drives have fixed media, while others let you swap out the storage. This is a key part of understanding PC components and how we keep data safe. Inside a computer, storage devices connect to the motherboard using SATA, that's serial AT attachment. Before SATA, there was parallel ATA, also called EIDE, which is now considered legacy. These interface standards set the rules for how data moves, how fast it moves, and even the shape of cables and connectors. There are three main SATA versions: SATA 1, SATA 2, and SATA 3. While the cables look the same, their data transfer speeds get faster with each version. Let's take a look at common types of magnetic media storage drives. First up, the hard disk drive, or HDD, the classic magnetic disk device many of us know. These drives can store anywhere from gigabytes to terabytes of data. Then, there's the tape drive, which you'll often find used for archiving. It works with a magnetic read-write head and a removable tape cartridge. Tape storage capacities also range from a few gigabytes to several terabytes. Both store data by magnetizing physical areas on the media, representing zeros and ones in binary form. SSDs come in three main shapes. First, there's the disk drive form factor. It looks a lot like a traditional hard drive. Then, we have expansion cards, which plug straight into the motherboard and fit inside the case just like other cards. Finally, there are M-SATA and M2 modules. These are smaller, use special sockets, and M2 is actually a standard for these kinds of expansion cards. SSDs store data using electrical charges in flash memory, making them much faster than magnetic hard drives. Plus, they have no moving parts, run silently, use less energy, and stay cooler. Let's talk about how computers get the most out of solid-state drives, or SSDs. The NVMe specification was created just for this. It sets a standard way for SSDs to connect with the PCIe bus and operating systems. This means SSDs can plug in without needing special drivers, making things faster and simpler. Then, there are solid-state hybrid drives, or SSHDs. They blend a traditional magnetic hard drive with flash memory, giving you a balance, faster than a regular hard drive, but more affordable than a full SSD. Let's take a look at optical drives, a key part of how we've stored and accessed data over the years. There are three main types: compact discs, or CDs, which handle audio and data; digital versatile discs, or DVDs, designed for digital video and data; and Blu-ray discs, which take things further with high-definition video and data. These drives use lasers to read and write information on discs. They were created to solve the storage limits we faced with older magnetic media like floppy disks. When we talk about optical storage media like CDs, DVDs, and Blu-ray discs, there are three main types. First, pre-recorded discs. These are read-only, so you can't change the data. Then, recordable discs, which let you write data once. And finally, re-recordable discs, where you can write and erase multiple times. For DVDs and Blu-rays, there's another important distinction: single layer or dual layer. Dual-layer discs nearly double the storage capacity, giving us more space on the same physical disk. Let's talk about video ports and cables, the connectors that link your monitor to your computer. You've probably heard of some of these. HDMI, DisplayPort, and DVI are common digital options. Then there's VGA and RCA, which handle analog signals. Thunderbolt comes in two versions here, 1 or 2, and the newer Thunderbolt 3. Each of these ports transfers video signals, sometimes analog, sometimes digital, or even both. Understanding these helps us choose the right cable for the best display quality. Let's talk about some of the other ports you'll find on a computer. These include the Personal System 2, or PS2, often used for keyboards and mice. There's the audio and game port for sound and controllers. Network ports connect us to the internet. Then there are storage-related ports like SATA and IDE, which link hard drives and optical drives. And of course, the Universal Serial Bus, or USB, which is everywhere. All these input and output ports let us hook up printers, scanners, and portable drives, the essential connections that keep our systems versatile. Let's talk about adapters and converters, the small but mighty components that help different technologies work together. Adapters physically connect one type of port or cable to another, like a DVI to VGA or USB to Ethernet adapter. Converters do the same, but they also translate signals between technologies, such as HDMI to VGA. With so many connection standards out there, these tools keep our devices talking smoothly, bridging gaps we often don't even notice. Input devices let us communicate with computers. They're how we tell machines what we want them to do. Some of the earliest and most familiar examples are the keyboard and mouse, which almost everyone uses every day. Then there are scanners, like ADF and flatbed models, which turn physical documents and images into digital files. For gaming, we have joysticks and gamepads designed to give precise control. And a KVM switch lets you manage multiple computers with just one set of keyboard, monitor, and mouse. These are the original building blocks of human-computer interaction. Let's look at some of the newer input devices that have changed how we interact with technology. First, the touch screen, a surface that responds to touch or pressure, making screens more interactive than ever. Then there's the stylus, which acts like a digital pen, perfect for artists and designers who want precision. Magnetic strip readers decode information from cards, like credit or ID cards. And barcode scanners quickly read product info, speeding up checkout and inventory. These devices expand the ways we connect with computers every day. Let's take a look at some newer input devices that have become part of our everyday tech. Digital cameras capture images and videos in a digital format, making it easy to store and share memories. Webcams are small video cameras built into or attached to computers, perfect for video calls. Signature pads let us sign documents electronically, saving time and paper. Smart card readers authenticate users through cards with tiny processors inside. And microphones let us speak to computers, turning our voices into digital commands. These devices expand how we interact with technology. Let's take a look at some of the newest input devices shaping how we interact with technology today. Near-field communication, or NFC, lets us tap to pay quickly and securely. Facial recognition scanners identify us by our unique facial features, while fingerprint scanners do the same using our fingerprints. Voice recognition picks out our voices, adding another layer of security and convenience. And then there are virtual reality headsets. These immerse us in games, simulations, and training programs, opening up entirely new ways to experience digital worlds. Let's talk about output devices, the tools that let us see, hear, or otherwise experience what a computer is telling us. These include monitors, projectors, VR headsets, printers, speakers, and headphones. What they all have in common is this: they take the computer's binary code and transform it into something we can understand: images, sound, or printed pages. Without output devices, all that data would just stay hidden inside the machine. Let's take a closer look at the main display technologies behind monitors and projectors. Most monitors rely on one of three types: LCD, LED, or OLED. When it comes to video projectors, LCD and DLP are the most common. DLP stands for digital light processing, a technology that uses tiny mirrors to create images. Another key factor in projectors is lumens, which measure brightness. The higher the lumens, the brighter the image, which matters a lot depending on your environment. Let's talk about the key difference between augmented reality and virtual reality. Augmented reality, or AR, layers images and sounds directly onto the real world around us, in real time. That means you still see your surroundings, with extra information right there. AR headsets don't block out ambient light, so you stay connected to your environment. Virtual reality, on the other hand, creates a fully simulated three-dimensional world. VR headsets cover your eyes completely, cutting off any view of the real world. Both rely on powerful PC components to make these experiences possible. Let's take a closer look at printers, those essential output devices that turn digital files into physical forms. There are several types: inkjet, impact, thermal, laser, and even 3D printers. They connect to our computers either through wires or wirelessly. Every printer needs some kind of material to work with: ink, toner, or liquid plastic, depending on the type. And behind the scenes, a driver helps the printer talk to the operating system. Whether it's a simple paper printout or a 3D object, printers bring our digital ideas into the real world. Speakers are one of the most common ways we get sound from our devices. Whether it's a computer or a mobile phone, audio is built right in, either on the motherboard or through a separate sound card. Then there are headphones, earbuds, and headsets. These all deliver sound directly to us, often wirelessly, using Bluetooth or Wi-Fi. They're essential parts of how we experience audio today. Now, let's turn to computer disassembly. This part is all about carefully taking a computer apart step by step, so we can understand how each component fits and works together. It's a hands-on way to see the inner workings, to learn what's inside, and why it matters. We're not just opening a box, we're uncovering the building blocks of modern technology. Now, let's dive into a video that walks us through the technician's toolkit. This segment shows the essential tools and techniques that keep everything running smoothly behind the scenes. It's a practical look at the skills and equipment that make a real difference when things need fixing fast. Watch closely. These are the hands-on details that bring our work to life. In this lab, we're focusing on safety, the foundation of any work with computer hardware. We'll start with personal safety, making sure you protect yourself. Then, we'll cover electrical safety, which is critical when dealing with power and circuits. Next, fire safety, because prevention and preparedness go hand in hand. Finally, we'll look at how to stay compliant with government regulations. Together, these parts keep you safe and your work secure. Now, we're moving into a video demonstration that shows computer disassembly in action. This is where theory meets practice. You'll see each step clearly, from opening the case to removing components safely. Watching this will help you understand not just what to do, but how and why. It's a hands-on look that brings the process to life, making it easier to follow along when you try it yourself. In this lab, we're going to take apart a computer, carefully and safely. It's important to use the right tools and follow all safety procedures closely. Before you start, get to know the tools you'll be working with. And remember, if you're ever unsure about a component or how to remove it, don't hesitate to ask your instructor for help. Safety and precision come first in this hands-on experience. We've reached the chapter summary, a quick look back at what we've covered. This is where everything comes together, highlighting the key points and main ideas. It helps us see the big picture before moving forward. Let's take a moment to reflect on the essentials so we're ready for what's next. In this chapter, we'll cover the essentials of personal computer hardware. We'll start by learning how to keep your computer components safe, because protecting your gear is just as important as knowing how it works. Then, we'll explore the features and functions of each key part inside your PC.